لأنه من الصعب جدا الواحد يعني يستوعب كل حاجة بالام ار اي، لكن يعني في الفترة هذه خاصة بالنسبة لكم ك يعني برايمري ييرز بالريزيدنسي بروجرام، فرصة ان الواحد يعني على الاقل يمر على الفيزيكس اوف ام ار اي. يمكن يكون هذه الشانس الوحيدة انه يعني تو تاتش الفيزيكس، لانه بعد كده حيكون مشغول بالكيسز وبالراوندز. فهي فرصة انه في الفيرست يير to يعني introduce you to the basic physics of MRI. احيانا قد ممكن تكون شويه صعبه، وبعض يعني الفينومينز او الاسبكتس تكون صعبه شويه، لكن يعني احنا يعني ممكن تشوفوا عندهم حتى انتنسيف يعني ماتيريالز اليوم، لكن الفكره الاساسيه انه على الاقل انه ناخذ touch of everything. راح نبدا ان شاء الله اليوم بالintroduction to MRI physics. حتكون عباره عن two lectures. المحاضره الاولى حتكون البيسكس ثيوري اوف NMR. يمكن تشوفوا شويه تغيير عن البروجرام اللي موجود عندكم، لكن هي المواضيع هي نفسها، لكن انا حبيت انها تكون بالطريقه هذه عشان يكون تسلسل يعني ماشي مع بعض. Let me just see, I can move this. Okay. Put it down maybe just to put this. طيب. If we start with historical background, احنا نعرف انه ال MRI was there long time before we use it in medical imaging. It was used as what we call it nuclear magnetic resonance, and it was used mainly in chemistry actually, since they have been using it for spectroscopy and analyzing materials. And the first scientist who introduced this to the world was Bloch and Purcell. That was in 1945. And then later on, 5 years, a new technique introduced to the NMR, which called spin echo, which most of us know this technique until today. And then in 1973, the first use of nuclear magnetic resonance in medicine, or in medical imaging actually, was in 1973. And that was achieved by 2 scientists. We have Paul Leatherpool in US, and then we have Peter Mansfield in Nottingham. And these 2 scientists, they managed to produce images for the first time in the history using this idea, which is nuclear magnetic resonance. These 2 scientists, they granted Nobel Prize in 2003 because of their pioneer work. And you can see the time between they discovered the MRI and the time they granted Nobel Prizes is long. There was a debate who's the one really introduced MRI. Is it American or English people? And then at the end, they managed to give it as a share between them. After that discovery, then MRI started to emerge. Too many applications. In 1976, Mansfield published maybe the first cross-section image through his finger. And in 1977, Damdian, he published the first whole body MR images. And this is the scanner that they use. It is in one of the museums in New York now. And as you can see, the images was not so good, but at the history, this is the first MR image ever. And let me just show you one interview done with Peter Mansfield. That was in 1980. As you can see, they don't know that time what is the consequences of exposing a human to this amount of magnet. Although this magnet is very, very low, he said it's like 1 Gauss or 10 Gauss magnet, which is too slow. For us, it's too low nowadays. But at that time, they don't know the consequences of exposing a human to the magnets. And then he said, if anything can happen, it's like cardiac arrest. I have, alhamdulillah, the chance to be one of the students to Peter Mansfield and Peter Morris. This is he was his student at that time, and then he was my supervisor. So that is the 1980 or 79 actually. Today, the technology is really developing very, very fast, and we have a new images. By the way, just remember those lectures today and tomorrow is for copyright. I mean, it's for your own use. Please don't put them in the internet. I'm not allowing anybody to put this in the internet. If you want to use it for yourself, that's fine. But please don't put it in the internet because they contain materials that have copyright again. So this is not legal. So please, if you want to use it for yourself, for your study, but don't put anything in the internet. I again insist that it is for your own only use. So as we can see, by that time, the technology developed too much, and then until we have today, cine images of the heart and for other body parts. Let us start with the physics of or the atomic structures of the MRI, of the idea behind MRI. As we know, the nucleus contains protons and neutrons. There are 3 types of motion present within the atom. As we all know, it is basics. We have electrons spinning on their own axis, and then we have the electrons orbiting the nucleus, as we can see there. I hope the movie is clear with you and the animation. So as you can see, the electrons, they are spinning around the nucleus, and then also they have another type of motion which they are spinning about their own axis. Then we have the nucleus itself, it's spinning about its own axis. So at the same time, we have the nucleus is spinning about its own axis. So these 3 types of motions producing signals. But what we are using in MRI is the last one, which it is the source of the NMR signal, which is based on the spinning motion of a specific kind of nuclei. We call them MR active nuclei. So what is MR active nuclei? Those nuclei are characterized by their tendency to align their axis of rotation with an applied magnetic field. So if we put those nuclei inside a strong magnetic field, they will start to rotate themselves with the magnetic field. So they will orient either parallel or anti-parallel, whatever. I mean, they will orient with the main magnetic field direction. So this is, for example, if they will start to orient with the main magnetic field direction. So the physical property responsible for this, we call it in physics magnetic moments of the nucleus. So it is a result of nucleus charge and spin, because nuclear has a charge, which is a positive charge, and then it's again spin about its own axis. This produce what we call force, or we call it quantum moment. So in physics, net spin or quantum phenomena is a property of those nuclei which contain an odd number of protons or neutrons that gives the nucleus the nature of net magnetic moment. So we will look to the nucleus as a small magnet. So imagine we have a magnet. Anything applies to the magnet will apply to the nucleus because it contains a small magnetic field. We are not talking about one nuclei. We have many nuclei in our body, and then adding those together will produce force, or will produce something can be measured. So this is, if we look them to the nuclei inside our bodies, they will at the end look like something like this. So what are the nuclei with potential use in the clinical studies? We have many nuclei. Actually, nuclei can be used in medical applications, not necessarily in imaging, but they can be used in other applications like spectroscopy and others. We have the hydrogen, which is the commonly used, and then we have carbon-13, nitrogen 15, oxygen, and then we have fluorine, sodium, and phosphorus. So those nuclei has the tendency to align with the main magnetic field. We call them MR active nuclei. If we put them inside a magnet, they will start to orient either parallel or anti-parallel to the magnetic field. They are, available with different concentrations. For example, in the nature, as we can see again, hydrogen is the more common and have abundant in a natural way. So we prepared some questions just to keep you with us. So I don't know if we can start the first question, which the source of the MR signal is the spinning. I don't know if it is. If you can, maybe I cannot, Doctor, you can start the poll from my side. I cannot start it. There's something wrong. No, it's okay now. Yes. So the first question, the source of the MR signal is the spinning of a specific kind of electrons around the nucleus, or the spinning of a specific kind of electrons around around themselves, or the spinning of a specific kind of nuclei about its own axis. So please answer which one you see it's appropriate. It's the only first question. Only first question, please. Okay, we will stop. So good, alhamdulillah. That's most of you. They said the right answer, which is the spinning of a specific kind of nuclei about their own axis. This is the source of the MR signal. So the hydrogen nucleus is the most MR active nucleus used for MR imaging because it has very abundant in our body, and also the signal having a single proton in the nucleus will give it a large force, what we can say a large magnetic moment, and therefore high MR signal. Imagine if you have a single person or a group of people. So it's easy to attract a single person rather than attracting a group. So since we have only a single proton, it's easier for the magnetic field or the external magnetic field to attract that protons because it's a single proton. And this is what makes hydrogen one of the common nuclei used in MR imaging. The other thing also, it's commonly available in our body. So it is in fat, in water, in protein, in muscles. So you see most of our body tissues containing hydrogen. We will go through some of the important phenomena in MRI. So alignment is what we call, if we put protons inside the magnetic field, as we just mentioned, they will start to align themselves, either parallel or anti-parallel. This is the same. We said at the beginning that we will look to the protons or to the nuclei as small magnets. If you put those small magnets inside a strong magnetic field, they will behave so either to go with the main magnetic field or to go anti-parallel to the magnetic field. So this is what happening. So if we push the patient inside the magnetic field or inside the magnet bore, so usually we represent the magnetic field, the main magnet, with the B naught. Some books in physics, they denote it as H, but in medical, physics, usually we use this B naught. This is the So before pushing a patient inside the magnet, the protons were oriented randomly. Once the patient inside the magnet, they will start to align either parallel to the magnetic field or anti-parallel to the magnetic field. As a result of this, we will have some protons going with the magnetic field and some going anti-parallel to the magnetic field. Finally, we will have, so this is an example. So the either orient parallel or anti-parallel to the magnetic field. Once the patient is inside the magnet, we say that the equilibrium state or the thermal equilibrium state, the magnetic moment of those nuclei aligned parallel to the B naught cancel out the small number of protons or magnetic moments aligned anti-parallel. So the number of protons will be almost equal between parallel and anti-parallel. So imagine this is the patient before we push him inside the magnet. And this is once the patient is already inside the magnet, patient or sample is inside the center of the magnet. As you can see, the protons will be oriented either parallel or anti-parallel to the magnetic field. And then we will have a small excess of protons which orient parallel to the magnetic field. So this excess of protons, it's a very, very small. We are talking about 1 per million, for example. If you have 2 million protons, you will have 1 million plus 1 in the parallel direction and 1 million minus 1 in the anti-parallel direction. So that excess of protons or the extra number of protons, we call it a net magnetization. And actually, this is the most important part in our whole story. So all of the MR signal will be using the net magnetization. The remaining, after we cancel the protons parallel and anti-parallel, the remaining number of protons are the source of our MR signal. This means this number of protons is very, very small. And that's why MR signal is very weak. So it's actually, we can say it's delicate. We need to deal with it with a very, very careful way to enhance it and to get something out of it. Another important phenomena is that we call precision. Again, as an analogy of motion of a spin top under the influence of earthly gravity, each hydrogen nucleus that makes up the net magnetization is spinning about its own axis. If we imagine, for example, if we throw we spin top, we throw it in the floor fast, it will start to rotate about its own axis, but after some time it will have an extra rotation. So it will have two types of motion. First, it will move about its own axis. The other one is, again, moving around the earthly gravity. So the influence of the main magnetic field, which we call P naught, produces additional spin or wobble around the M naught or around the M naught, اللي هي main net magnetization for the M naught around P naught. This spinning is called precession and causes the magnetic moment to follow a circular path. So this is the one I make it just to make the things understandable. The small circle is the spinning of the proton about its own axis. The large circle is what we call the precessional path. The protons, once we put them inside the magnetic field, طبعا we are talking about the net magnetization. هذا احنا كنا ننسى البروتونز اللي parallel و anti-parallel. احنا ويانا concentrating على net magnetization only. So once we push the patient inside the magnet, those protons اللي هم net magnetization, they will start to have two type of precession or motion. أول حاجة حيبدأوا يدوروا حوالين نفسهم. الحاجة الثانية حيبدأوا يدوروا حوالين main magnetic field. We call this as a precessional frequency. And also we noticed, actually, Larmor, scientist Larmor, he noticed that as we increase the magnetic field, this precession will become faster. يعني كل ما زودنا المجال المغناطيسي كل ما صارت هذه circle rotation about the main magnetic field faster. And he came up with his equation. Now, question number 2, we will go to the bulletin. Net magnetization represent the total number of protons or M-active protons, or the result of the protons remain after parallel protons cancels out the anti-parallel ones, or the total number of protons oriented parallel to the main magnetic field. Let us see, sorry. So now question number 2, net magnetization. If you can relaunch, I think we have to. The ball doctor are supposed to be each one separate. يعني كل question كان المفروض يكون لحاله. Let us ignore question number 1. Go to the number 2. زي ما قلنا, which one you think it is the right answer? Only question number 2. Please ignore 3. I mean, there was something wrong with the questions. We're supposed to be each question separate. So, share the results. So most of you, they said it's answer number 2, which is the right one. So 2 is the correct one. Net magnetization, as we mentioned, after we put the patient or the sample inside the magnet, the protons, they will start to cancel each other, and then we will come up with the net magnetization after canceling the protons. Another important thing is the precision, as we said. Once we saw the protons go back there, the net magnetization will start to process about the main magnetic field, and that circular, that path is circle, and the speed of the protons will, as we said, depends on the strength of the magnetic field. This is called the precessional frequency, and we call it then Larmor frequency. The unit of the Larmor frequency is megahertz. Now, anything goes in a circle. Instead of we say this is a speed, we said the frequency, because it goes in a circle. Start from the same point and go back to the same. So start from one point and come back again to that same point. So instead of say speed of the protons, we say the frequency of the protons. Now, the frequency of those protons is measured by hertz. Actually, hertz is a physical quantity which actually represent. We can say it's circle per second. So 1 hertz equal completing 1 circle per second. Now, the protons, they completed 1 million cycle per second. And then we said it's 1 megahertz. So the protons or the nucleus, هنتكلم عن البروتونز. الهيدروجين ما فيه إلا بروتون واحد في النواة، عشان كده احنا دائما we say the protons. But actually it's the nucleus. So they completed 1 million cycle. So عشان كده احنا قلنا 1 megahertz is the speed or frequency of the protons in the main magnetic field. So that's the spectrum of frequencies used in medical imaging. As you can see in X-ray, we use 10 to the power of 18, and then in visual imaging 10 to the power of 14. As you can see, the MR imaging has the lowest frequency in the medical imaging, and then that's why we call it is safe. It is not using any invasive frequencies or energy. So that is the MRI. It is in the we use the radio waves. Actually, radio waves is what we are using commonly in our radio stations. So that is a safe range of frequencies. So the value of that precessional frequency is governed by Larmor equation. So as we said, he noticed that as we increase the magnetic field, the precessional frequency will increase, and then he put that equation. Now that equation shows that there's a proportional between a frequency and the magnetic field, and we use the constant, which is gyromagnetic ratio. So this means that this relation is based on that specific nuclei. And for example, if we put the hydrogen in a magnet with a strength of 1 Tesla, the protons, they will start to precess with 42 megahertz. Now, B0 is measured in هنا قلنا بنقط هي strength of the main magnetic field. It's measured in Tesla. 1 Tesla equals 10,000 Gauss. So we have 2 units for magnetic field strength. Tesla is the strongest, used for the strongest values, and Gauss is used for small values like Earth gravity. For example, the Earth gravity at the surface of the Earth is equal 0.5 Gauss. And imagine that you have a 1 Tesla magnet in your hospital. This means it's equal 20,000 times Earth gravity. So it's a huge amount of magnetic field, and that can cause sometimes disasters like what we can see. So there are many accidents happen because we are using a very strong magnetic field. There is no radiation, as we said. MR used very low frequency and energy, but at the end there is a problem with a strong magnetic field which can cause danger or can cause an accident. That constant is called the gyromagnetic ratio, and it's a constant of proportionality. It is, as I said, for hydrogen, it is a 42.57 megahertz per Tesla. For other nuclei, they have different constants. So that equations is general. If you want to use it for hydrogen, you just replace that one with a 42.57, that constant. Then you can put 1 Tesla, 2 Tesla for every magnetic field strength. You can calculate the frequency. So if you put the hydrogen, for example, 1 Tesla, so this is 1 multiply 42.57, you will get the frequency of the hydrogen at 1 Tesla. So, sorry, this is, for example, field strength, 0.5 Tesla. The proton will process with 21 megahertz. At 1 Tesla, it will process with a 42.6 megahertz. At 1.5, it will process with a 63.9 megahertz. Another, again, important phenomenon, which we call it resonance. So an MRI resonance is the induction of a transition between 2 different energy levels. Okay, no problem. So the energy required to produce such a transition in a magnetic resonance is the difference in magnetic energy between the lower and upper energy levels. In physics in general, to produce, for example, excitation or response, as we use, for example, in X-ray tube or in the neon lamp, we try to make difference between the anode and cathode, and the electrons will move from anode to the cathode, and then when they go back to their equilibrium state, they will generate X-ray. So we have to make sure, so we have 2 different energy levels. The first energy level is those protons going to the direction of the main magnetic field. And the other level is those protons going anti-parallel to the magnetic field. So we have two energy levels. If we manage to move the proton from lower energy level to the higher energy level, then we will make a transition. So for hydrogen, we have 2 levels only. So those parallel to the magnetic field and those anti-parallel to the magnetic field. Other more complicated nuclei like sodium or phosphorus, they have more than 1 proton, so in their nuclei. So they have more than 1 transition. So they can, for example, 1 proton can move from the very high level to the less level. So for example, you have that with the 3 protons. So there are many chances. This can be translated. I don't want to take you too much in complicated things, but this is in spectroscopy translated to the line, number of lines. Hydrogen usually represented in spectroscopy with a single line. And phosphorus, for example, is represented by 3 lines. This means that there are three transitions. For us as imaging, we use hydrogen, so we have only 1 transition from the upper energy level to the, we call this is lower energy level, because the protons, they are going with the direction of the main magnetic field. And this is the higher energy because the protons, they are going against the direction of the main magnetic field. So those are in the higher energy level, and this is in the lower energy. If I want to make a transition, first I need to give an energy to that proton, so to move it to the higher energy level, and then leave it to return. During that process, we can measure something and we can get some signal. Now, the difference between the upper and the lower energy level is called delta E, so we have to give enough energy to the proton to be able to move from the lower to the upper energy level. To do that, or to make the protons move from the lower to the upper energy level, we have to satisfy two conditions. First, the frequency of the externally applied energy must match the Larmor frequency. احنا قلنا في البداية إنه once we put the protons inside the magnetic field, they will start to rotate with the main magnetic field with a frequency depends on the main magnetic field. Now, if I want to talk to that proton, I have to talk to him with the same frequency. So, for example, if I put the protons in 1 Tesla magnet, they will start to rotate in 42 megahertz. To attract that protons or to give him an energy, he will only understand energy with the same kind of frequency. So I have to give a 42.57 megahertz frequency so the proton can respond. If I give more or less frequency, it will not respond. So this is the first condition. The second condition, also the applied external energy must be applied at perpendicular direction. I have to give that external energy اللي هنسميها later on B naught عشان نميزها عن المين ماجنتس. المين ماجنت سمينا B naught. الاكسترنال انرجي اللي راح نعطيها للبروتون هذه عشان ننقل البروتون من اللور الى الهاير انرجي هنسميها B1 سميناها external energy. It must be applied as a perpendicular to the main magnetic field. So as you can see, that is the main magnet field direction. The protons or the net magnetization, they are precision about main magnetic field. Now we will give an external energy. So we denoted that with B1. To have a resonance, معناته إنه البروتونز تستقبل أو تتقبل الانرجي هذه, that frequency must match the Larmor frequency. احنا قلنا Larmor frequency 1 Tesla هو 42 megahertz. معناته هنا we have to give the similar frequency. If I give higher or lower energy frequency, that will not affect anything. Other thing, it has to be perpendicular. Again, if I give it with the same direction, this means I'm increasing the main magnetic field, so the proton will start to process faster. That's the only thing will happen. So it has to be applied perpendicular to the main magnetic field. So question number 3. Now we have 2 units in magnetic field. We have Tesla and Gauss. Which one do you think it's correct? 1 Tesla equal, let me start the poll first. So question number 3, is it 1 Tesla equal 1000 Gauss, or 1 Tesla equal 10,000 Gauss, or 1 Gauss equal 1000? So question number 3, please. So most of you are right. The answer is number 2. So 1 Tesla equal 10,000 Gauss. Okay, that's the end of part 1. As I said, if there is any question, I don't know, Dr. we can open for the basic things. Any question? I don't know if you can.
عندنا دكتور الشات اللي عنده أي سؤال يقدر يطرحه في الشات على دكتورنا.
ممتاز. So we'll give 2-3 minutes again to for questions. أنا ما طلع عندي الآيكون حق الشات ما أدري ليش.
الشات يطلع ظهر على الجنب.
ايوه موجود.
تحت دكتور مع البول وهذه الاشياء.
ايوه واضح الان.
اي في سؤال دكتور هنا.
طيب هنا السؤال يقول لي what determined if hydrogen protons align parallel or anti-parallel to the main magnetic field. This is physical phenomena. Again زي ما أنت لو جبتي small magnet عندك حطيتيهم على الطاولة مثلا وجي قربتي strong magnet عليهم راح تلاقي إنه some of them they will attract in parallel. This is a quantum physics. Some of them they will orient parallel, some of them they will anti-parallel. ما حنحصل البروتون oriented perpendicular لا كلهم حيكونوا بالاتجاه هذا لكن حيكونوا exactly half. الفرق حيكون إنه عندنا البروتونز اللي ماشيين مع الماجنت حيكونوا a little bit extra. يعني قلنا little bit معناته إنه very little 1 per million. So that's ال 1 per million هم المحصلة أو اللي سميناهم net magnetization that we are going to use them in medical imaging. So this is a physics, we call them quantum physics that decide which probability of having the protons in the lower or in the higher energy. Any other question? Question is when we make the B1 parallel with the proton, so we make the precession faster. Yes, that's true. يعني لما يكون ال B1 parallel to the main magnetic field ما راح ينتقلوا هم ما راح يتحركوا البروتونز بس حيصيروا they persist faster. So it's not, this is not what we need. We need to move them from the lower to the higher so we can see their response. This is the resonance. Okay, good. So I think the nuclei must contain odd number of protons to use them. Yes, that's true. Odd number of protons or neutrons. It's to be يعني حتى عشان نقدر نسميهم MR active nuclei. طيب. We will move to the second lecture. 1 second, please. So now we will concentrate on the MR signal. So we agreed that having the protons in the main magnet will generate net magnetization. That net magnetization is the source of our MR signal. And then the behavior of those net magnetization is what we're going to measure in our MRI images. So the source of the MR signal is the net magnetization. The generation of the MR signal is analog to the generation of electricity in dynamo. So imagine you have a magnet and you rotate that magnet inside a coil, that's electric wires, any forming coil. So moving that proton this way will generate electricity. In our case, that magnet is the net magnetization. If we manage to move that net magnetization across an antenna or coil, we will be able to generate electricity or signal. So that is the magnet, moving that magnet across the coil اللي هو حنسميه في المستقبل حنسميه ال RF coil اللي هو ال RF antenna اللي هو حنستخدمه عشان to pick the signal from the patient. So the rule of the RF pulse is to cause the net magnetization to rotate away from its equilibrium alignment along Z-axis. طالما انه البروتونز في الزد اكسس they are useless ما حنستفيد منهم لازم نحاول نبعدهم عن المين ماجنت عشان نقدر نشوف their rotation عشان نقدر to measure their rotation or their response. طالما هم بالزد اكسس ما حيكون في عندنا this is thermal equilibrium في اي يعني physical system thermal equilibrium هو وضع الريست وضع فبالتالي ما هو احنا we have to do some perturbation to that equilibrium state عشان نقدر نشوف response. So what we need is to take those protons away from the main magnetic field. That is done by sending an external energy تحقق نفس الشروط اللي تكلمنا عليهم قبل شوية انه يكون لهم same frequency as Larmor frequency. اذا احنا نستخدم 1 تسلا ولا 2 تسلا ولا 3 تسلا لازم نعرف كم المagnetic field اللي احنا نستخدمه وكم الفريكونسي اللي هو Larmor frequency. Then we use external power energy to excite the protons. So that external energy, it has to match the Larmor frequency. Once we apply that energy, as you can see, that is the external energy, using the same frequency as laminar frequency. We call this is B1 and that's B0. That is perpendicular. The protons, they will start to rotate. Now, as you can see, they will not go direct from B0 to the transverse. They will go in a solenoid shape or helical way. They start from B0 and then they continue. As we give more energy, they will start to continue. But if we stop at this point, the protons, they will lie on the transverse plane. This means they will start to rotate in that plane. Once that energy finishes, they will go back to their equilibrium. اللي هو ايش equilibrium? They will go back to the Z اللي هو B0 direction. So that net magnetization, we give a short excitation using an external any power supply or any coil, and then that will cause the protons to rotate until they reach there. If you give more energy, they will continue to go to the minus Z. But احنا نبغاهم ينزلوا هنا على الترانسفيرس. ليش؟ حنشوف الآن. So that's the protons. They will fall there, the transverse. As you can see now, every time they pass through that coil, they will generate signal. That signal is the MR signal that we want to measure. So once the net magnetization is in the transverse plane, it persists about the direction of the main magnetic field. هي قاعدة تدور زي ما قلنا تبرسس. احنا الفرق الوحيد انهم بعدناهم عن الماجنتيك فيلد. هم كانوا يدوروا حوالينه بشكل ملاصق. الان احنا بعدناهم عن المين ماجنتيك فيلد. هم they still persist لكن in the transverse plane. So this is again, we can, maybe it's easier to imagine. Let's see. No, it's not showing. Something wrong, I don't know why. If I go out. Something wrong with the animation anyway. But what, the idea is that the proton, they will start to rotate perpendicular to the main magnetic field direction. And then if we have a coil presented at that point, it can see the signal. So hopefully this will yes, for example, that is the net magnetization. Now it's in the transverse plane, it will start to rotate. And that is the receiver antenna or the RF coil. It is used to send energy and at the same time can be used to detect the response. So the protons now in the transverse, they start to rotate, and that's the measured signal. Every time you have like positive and negative poles of the magnet, and this can be measured as a signal. So this voltage establishes the MR signal, and that's what we can see. I don't know why those videos are not. Usually they work, but maybe because of the Zoom something. Okay, so question number 1 now. Maximum MR signal is generated following, if we go back to that shape-led excitation, we put the protons in the transverse مثلا, and then we have an antenna or coil can detect. So maximum signal can be detected immediately following the 90 degree or 180. طبعا نتكلم عن الديجري اللي هي amount of rotation. So 90, 180, or 180 followed by 90. So which one you think? This is question number 1 only, please.
البول الثاني جاهز دكتور.
ممتاز. So 30 seconds, we will stop. Okay. Now ما ادري انتوا ما حد
ما دخلوا على البولينج. ادخلوا على البولينج.
Okay, so let's relaunch again.
ايوه.
الان we have 30 seconds. Please answer the question.
دكتورة إذا ما عليك أمر البول ما يطلع submit, we just select صح؟
Select and then start. يطلع لي أنا button start pull. So they supposed
ما
to.
يطلع لنا. أنا يطلع لي 1 2 3 questions multiple. بعدين submit you can't submit.
هو you have to do them one by one عشان ما يبقوا كل الأسئلة مع بعض أحسن بحيث إنه يكون only one question at a time. You do one and then save and then go another one save.
Okay.
طب أوكي الآن I don't know maybe something wrong. Anyway, so the maximum signal generated following 90 زي ما قلنا 90 here. Okay, it's the so 90 is the maximum signal because the protons, most of the protons can be seen by the antenna. If we, like, for example, used a 45 flip angle, only partial of them, only half of the protons will be seen. If we use a 180-degree RF pulse, this means zero. We will not see anything because all the protons are in the z-axis. So the maximum MR signal is generated following the 90-degree because, let's say, most or the majority of protons will be in the transverse plane. Okay. So free induction decay. So when the externally applied RF field is switched off, the component of the net magnetization in the transverse plane is subject to the main magnetic field, and it starts to persist about it and lose the energy given to it by the RF pulse in a process called relaxation. So imagine those the protons, now they are in the transverse, they will start to lose the energy slowly as we will have that shape. We call this is a free induction shape or exponential decay curve. As you can see, let's just repeat this. This is immediately will be very high. By the time they will start to lose their energy and the signal goes to zero. So this is called relaxation or losing of energy. So it happens as a result of the protons return to their equilibrium. اتفقنا عليها قبل شوية اللي هي equilibrium state إنه they will go back to their original location اللي هو ال B naught, and the component of MXY اللي هي في transverse it start to decrease. So imagine this is the protons now. I don't know why the presentations, I mean, some of those animation, you can see them or still black? And for me, they're showing just black.
It's still black.
That's something wrong, I don't know why. Anyway, so. So as MXY decreases, the magnitude of the induced voltage in the receiver coil decays. So this decay is called free induction decay. So for example, if the antenna is in the transverse, it will see the protons, plus, minus, plus, minus, plus, minus, and the amplitude also will start to decrease. Why plus and minus? Because, as I said, it's a magnet. The net magnetization of the magnet has two poles, plus, minus. So it rotates. When the plus part of that, any plus pole, for example, comes near the coil, it will give us maximum signal, and then it will rotate minimum, maximum, minimum, and also the amplitude starts to lose. Why it starts to lose? Because the protons, they start to go to their equilibrium net magnetization. And this is, for example, this is immediately after the excitation, the protons in the transverse. So imagine the coil is located at this point, it will have plus minus, but the things will not go forever like this because the protons, they start to lose their energy and go back to the z-axis. So we call that a relaxation because the protons, they lose the energy and they go back to their original location. So why relaxation happen? So relaxation is a process that happened after the terminating of the RF pulse, in which the physical changes that were caused by the RF pulse return to the state they were before the application of the RF pulse. So spin relaxation is caused by the exchange of energy between the spins and between a spin and another. احنا نتكلم على millions of protons. كل واحد حنسميها spin, يعني proton واحد حنسميه spin. So interaction between the spins, يعني between the spins, each others, and between the spins and the surroundings. Also, يعني the proton, they are not alone. They are surrounded by other atoms, and by the, again, outside, it's shielded by electrons. Electrons has a very high energy compared to the protons. It's like 1,700 times the charge of the proton. So that can cause lose of energy. So that's why the protons, they start to lose the energy and go back to the z-axis. So these two interactions give rise to two types of relaxation. الأول اللي حنسميه spin relaxation or T2. T2 relaxation is caused by the interaction between spins each others. يعني لما تكلمنا إنه عندنا كل بروتون في بروتون جنبه حواليه وبالتالي this cause local نسميها distortion to the magnetic field or loss of energy. So after terminating the RF pulse, due to the slight variation in the nuclei local magnetic field, some nuclei experience slightly stronger magnetic field and persist faster than those experienced. So بدل ما كانوا هم already in phase or as a group, they will start to lose that uniformity. So they will start to become more and more groups, as you can see. So they start to have 2 groups and then 4, 8, 16, until we have every proton has another proton opposite to it. So this will cause a dephasing or cancellation of signal. So the reduction in the net transverse magnetization causes a signal to lose, and this dephase is called a transverse T2. So this is immediately after the excitation. We will have 1 group, as you can see, then 2 groups, then 4 groups. The more time, more dephasing, and then at the end we will have 0 signal. Why? Because each proton has 1 opposite to it, and then that will make the signal vanish or destroy. So the more time, more dephasing. طبعا احنا نسميه الايكو تايم حنتكلم عليه بعدين حنيجي, لكن هو time is very critical because as you can see, more time, more dephasing, more signal loss. So the rate of that decay, if we want to measure the rate of the decay, it's exponential process. يعني معناته انه they are not linearly decreasing. مش انه بعد هنا the first milliseconds حيكون عندنا 100 بعدين the second milliseconds حيكون 50. لا, they're going as an exponential. So the constant of that decay اللي حنسميه احنا constant of decay of that T2 relaxation, it is the time takes 63% of the transverse magnetization to be lost. If we see that graph, the protons in the transverse, all of them now in a one single value مع بعضهم الآن موجودين. بعد شوي حيبدأوا يصيروا dephasing, تصير more groups, more and more groups, until eventually we have infinity number of groups. كل واحد حيكون group في جهة مقابلة, وبالتالي the end result here is 0. Now, as I said, we have to translate this to values. And let us see, hopefully that will work. I don't know, all those animation, they are not working. I'm not sure why. In the break, we try to do something. Okay. Yes. So as you can see, we have to translate this to value. يعني زي ما نتعامل مع المشكلة هذه. This is, for example, this is a computer will not understand curves. We have to give him a value. So each tissue has a way of dephasing. If we take, for example, the hydrogen, it will start from 100 and then start to lose in this way. الفات مثلا, it will start to lose faster. البروتين, it will have slow. So each tissue has different way of dephasing, أو نسميها إحنا signal decay. We want to translate this to value. We asked those in mathematics. They told us each exponential curve can be translated or can be represented by constant. زي ما عندنا مثلا الخط المستقيم في الماثماتكس, احنا نميل الخط المستقيم له معادله لحسابه. نفس الحاجه الكيرف له معادله لحساب الكونستانت اوف ديكي. طبعا المعادله هذه بتقول لنا انه الكونستانت هو التايم اللي correspond if you lose 63%, معناته حيبقى عندك 37 بس. التايم correspond to that is the constant of that curve or constant of decay in this any case constant اللي هو نسميه ايش T2 relaxation. As you can see, we have two tissues. They have different way, or they will behave different, and then the constant of the first curve is different than the constant of the second curve, which represents another tissue. This is again representing the story from the beginning. Immediately after excitation, the protons, they start to dephase. Now they start to, but we cannot tell which one is dephasing faster. But as the time increases, we can see that tissue is dephasing much faster. If we draw this by a curve, we will be able to see that that tissue is dephasing faster, and it has a constant of, or we call it T2 relaxation, compared to the first one. Now, T2 relaxation time vary from tissue to tissue, and therefore the numerical values of the T2 is a characteristic of a specific tissue. Typically, T2 in biological tissues spans a range from about 50 to 200 milliseconds. And this is an example of some tissues in the brain, for example. And white matter has a 67 milliseconds, means it will lose 63% of its quantity or value in 67 milliseconds. While the CSF takes longer to dephase, it takes 280 milliseconds to lose 63% of its original value. The other type of relaxation is called the spin lattice relaxation. طبعا الكلمة هذه شوية صعبة وغريبة. ليش؟ لأنه إحنا قاعدين نستخدم الفينوميناز أو المفاهيم اللي كانوا يستخدموها بالكيمستري. إحنا نعرف إن MRI هو أصلاً generated originally for chemistry. اللاتس اللي هي البلورة، كانوا بيحسبوا البعد البلوري في الكيمستري، فبالتالي إحنا ندرس العلاقة بين البروتون والمحيط الخارجي له. ثم البروتونز، المحيط الخارجي اللي هو الالكترونز، الاذر نيوكلياي. سو بالتالي انهم الاذر protons and the other atoms, electrons, those will cause the energy again to be pulled from the proton, and this will cause the protons to relax and go back to the z-axis. And again, if we study the behavior of the proton, it's an exponential process. It's not a linear. معناته إنه مش إنه after 1 milliseconds حيكون رجع 5%، بعد 10 حيكون رجع، لا. It's exponential. So if we want, this is, unfortunately, those are very valuable presentations, but I'm not sure why it's not working. So at the end, all of the protons, they will go back to the z-axis. So again, if we draw a curve, we will find that is an exponential curve. The nice thing in this graph or figure shows that the protons, they will not come as a unit, because احنا قلنا في البداية انهم they will have a T2 or transverse relaxation، معناته انهم حيصير لهم زي dephasing، انه يعني they will يعني بدل ما كانوا في one group they will become more and more groups، وبالتالي كل واحد منهم حيرجع من جهة مختلفة. واحد حيرجع من الرايت، واحد من الليفت، ومن هنا. وبالتالي if we look to them as we يعني as a cone، بالنهاية كلهم في النهاية حيرجعوا إلى the z-axis. So T1 relaxation involves the release of excess energy absorbed by the spins from the RF pulse to the molecular environment or lattice. The rate of recovery is an exponential process with a recovery time constant T1. يعني هون لو جينا رسمنا الجراف أو الكيرف هنلاحظ إنه that signal start، يعني هنا معناته كل البروتونز موجودين الآن في الترانسفير، كذا ما في بالزد axis no more any signal. Okay, let's start again. Okay, so they start to recover until all the protons return to the z-axis and no more protons in the transfers. That is what we call exponential curve. It's again the same idea we said in the transfers. It's applied for the longitudinal relaxation. So if we want to calculate the constant of recovery for this curve, we will calculate 63%. The time correspond to that is the T1 constant recovery or T1 relaxation constant for that tissue. T1 relaxation times again vary from tissue to tissue, and therefore the numerical values of T1 is a characteristic of a specific tissues. it has been also found that T1 values depends on the applied main magnetic field. زي ما قلنا إنه عندنا كل tissue لها ترجع it will behave in different way. فبالتالي الفات راح يرجع بشكل جدا fast compared to the CSF or compared to the protein or other tissues. الوايت ماتر جراي ماتر كل واحدة منهم لها T1 constant مختلف عن الثاني. Also the scientists they found that the strength of the magnetic field also will affect this value. يعني لما أجي أنا measure ال T1 for the fat at 1.5 I will find it different than the T1 in a 3 Tesla for the fat. يعني حيكون الفرق يعني بينهم حوالي مثلا في 1.5 هو 150 في ال 3 Tesla it is 200. ف T1 relaxation times affected by strength of the main magnetic field and this is logic. ليش؟ لأنه strength of the magnetic field will make the protons persist faster. صح؟ لأن احنا قلنا كل ما زاد المجال المغناطيسي كل ما صار persistent faster. Now, when the magnetic field is higher, the protons they will persist fast. Then, if we stop the excitation energy, معناته عملية الرجوع حتكون أسرع وبالتالي they will cause faster relaxation. So this is معناته they will take more time لأنهم قاعد يدوروا بشكل سريع. They will take more time to stop. So this is the T1 relaxation in a 3 Tesla is larger than T1 relaxation in 1.5 Tesla. So this is an example of some T1 constants for some tissues in the brain. White matter, for example, 510, CSF 2650, and then you can see the variation between this. So this means as the tissue is more in general, and as it's more fluid, it takes more time to relax, to go back to the Z-axis. نفس الكلام بينطبق على T2. كل ما كانت tissue more fluid, كل ما كانت takes more time to ايش؟ to dephase. يعني هنا بنتكلم عن 280 معناته انه even after 280 millisecond we still can see ايش؟ some unity of the protons. مجموعات من البروتونز لسه ما صار لها dephasing. نفس الحاجه بالنسبه لل T1 البروتونز are taking longer time to recover to the Z-axis. هذه الفاليوز مهمه جدا بالنسبه لنا لان بعدين راح نستخدمها to translate tissues الفاليوز هذه الى tissue contrast. I'm not sure why this is not working, but so question number 2. Let's read it first before we start the poll. T2 relaxation is a result of interaction between parallel and anti-parallel protons. نتكلم عن T2 relaxation ولا interaction between protons in the transverse direction ولا interaction between protons and their surrounding. So which one you think? This is the question number 2. Can you please answer? You can see the question? Yes, good. I can see some people already answered.
Yes.
But why not everybody interacting? Only question number 2, please.
لأن دكتور بعضهم ما يطلع لهم البول.
غريب.
عندهم مشاكل في البول. لأن اللي داخل من الآيباد اللي داخل من اللابتوب زي كذا دكتور.
أنا جربته على جوال شغال، جربته على كمبيوتر.
إيه هو في ناس يطلع لهم وناس لا. في ناس حيكون ذي والبارتيسيبيتين في الشات دكتور ممكن نشوفهم.
هو طبعا ميزة يعني كيف احنا في الاونلاين تيتشنج صعب انك يعني ما تعرف الريسبوند اوف يور اودينس هل هم فعلا they are understanding and catching. البولينج is really excellent way to see this.
ايه عشان
anyway I can see more people they are going toward number 2 which is the right thing. So transverse represent interaction between the protons in the transverse direction. معناته انه so 2 is the right answer. So proton density. Now we talk about the signal characteristic. تكلمنا على T1 قلنا انه is measure of the protons relaxation or recovery to the Z-axis. T2 relaxation it measures the dephasing of the protons in the transverse. Now we will talk about the proton density. Proton density represents the number of MR active protons in a unit volume of tissue. and it's usually expressed as a percentage of the proton density of water. يعني كل ما كانت التشو فيها more protons, it has higher proton density. زي مثلا نتكلم على CSF, it contains more number of protons, وبالتالي we expect it to have a higher proton density. Sometimes it's represented as NH number of protons. So proton density generally increases with water content. Proton density varies among different tissues by only a few percent. عشان كده احنا دائما ما يعني البروتون density is not used too much في الاميجنج especially في MSK في الماسكوسكليتال، لكن في النيورو مثلا في الابدومن نادر تجد لها ابلكيشنز، يعني ابلكيشن قليله جدا لانه الكونتراست فيها is not too much high compared to the T1 زي ما شفنا قبل شويه. T1 كم كان بالنسبه الوايت الفات او الوايت ماتر جراي ماتر compared to the CSF الرينج جدا عالي. ف this is for example some tissues different between the white matter, gray matter and CSF. You see الفرق بين T1 كم يعني كم أو T2 بينما هنا it's a few percentage, which is that's why we are not using it too much يعني as a contrast. So as the number of MR active protons aligned with the P naught increases with the increasing P naught معناته إنه again increasing the strength of the magnetic field will increase البروتون دنسيتي، وهذه حاجه جدا مهمه لانه عشان كده احنا دائما نستخدم we prefer مثلا 3 تسلا in some applications. Why? Because it provides us with more number of protons, so more net magnetization, وبالتالي البروتون دنسيتي حتكون اكثر. So tissues اللي فيها less number of protons they will have more signal, and then we can see those tissues much better in high field لانه they have higher proton density. Sorry. So at the end of this part, we will talk just about the phenomena or idea of a spin echo. So a spin echo pulse cycle consists of a 90-degree RF pulse followed by one or more 180 RF pulse, where the signal is measured after each 180 RF pulse. So for example, this is يعني دائما احنا مثال حق اللي هو الفاست وسلو. Is playing, yes. So at one point we will invert the direction of motion. We can see that is the, for example, this is this is slow protons and this is fast protons. If we flip the direction of motion, we will be able to generate again a point where we can see both slow protons and and fast protons. So they dephase now, they start to dephase, which we call a T2 relaxation. At one point, we can apply a 180, it will cause the protons to again to rephase. So that can be again described. Unfortunately, all of these, anyway, those, and you can find them in the nets. So in MRI practice, they're really nice presentations. So the time interval from 90 pulse to the first 180 pulse must equal the time interval from 180 to the يعني generation of signal. This is a diagram هذا أنا رسمته مثلا. هنا immediately after the 90 degree البروتونز موجودة في الترانسفيرس تبدأ يصير لها dephasing. Now at one point if I apply a 180 إيش معنى 180؟ معناته أنا give double the energy اللي أعطيتها بالبداية. 90 degree هي حركة البروتون من الزد إلى الترانسفيرس. هذه ال 180 معناتها حتحركهم من الترانسفيرس الى الاوبوزيت دايركشن، يعني هم حيتحركوا مش من تحت يروحوا الى الجهه الثانيه، وبالتالي الان اللي حيصير البروتونز اللي كانت فاست اللي في البدايه راح تصير في الاخر، والبروتونز اللي كانت سلو اللي كانت في الاخر راح تصير في البدايه. بدل ما كان عندنا هنا دي فيزنج زي ما نشوف كان دي فيزنج، راح يصير عندنا اجين ري فيزنج وتبدا تتكون السيجنال مره ثانيه. So this will cause the signal to rebuild and we will have a new signal. That's why we call it a spin echo. So a spin echo causing the protons to again gather again, and that will cause a spin echo. احنا تكلمنا في البداية على الهيستوري قلنا spin echo introduced by Erwin Hahn. Erwin Hahn, he was an undergraduate student. يعني you see يعني he was an undergraduate and he introduced this idea and still used up to date. The idea is actually you can regenerate the signal of the MR signal by applying a double energy which can cause the protons to move back to the in phase status. So again, that's dephasing, and then at one point we will send an 180 degree. This means we'll flip the protons, and then that will cause a rephasing of the protons, and then we will generate the signal again. Yeah, this again, just so 90 degree, it will cause the tissue, the transfer, they start to dephase. At one point, we will apply a 180, means the protons, they will move all the way to the other direction. And in a state of dephasing now, they will start to have three phase, and the signal is generated. We call this a spin echo. An important thing in that cycle, this one, sorry, is the time. As you can see, 180 RF pulse, we call it a refocusing RF pulse. نعرف في الفيزيكس عندنا العدسة اللي هي المسميها عدسة مجمعة refocusing pulse, refocusing lens. إذا تحط الأوبجكت هنا تكون الصورة على نفس المسافة من اللينز في الجهة الثانية. فعشان كده سميناها 180 refocusing pulse، لأنه حيتكون عندنا السيجنال على نفس المسافة من ال 180. فبالتالي we call this echo time. The echo time equals double the time from 90 to the 180. This is called اللي هو echo time. Echo time is important ليش؟ لأنه it's an important factor في image contrast. So question number 3, which of the following will increase net magnetization? RF pulse ولا proton density available ولا T1 and T2 relaxation؟ احنا تكلمنا عليه انه which one of those will. So question number 3, please, if you can see it. Is it the RF pulse or the proton density or T1 and T2 relaxation? يعني أنا في number 1 and number 2 many people they are يعني هو to be honest the right answer is the number 2. So number 2, why? Because the proton density, as we said, more protons means more net magnetization. عشان كده قلنا 3 تسلا حيكون أحسن. ليش؟ لأنه يعطينا more proton density, more net magnetization, and then we will have يعني better signal. So number 2 is the right answer. Okay, now we finished the second part. I don't know if we will give like a 15 minutes break. I don't know, I'm not really going good with the time, but we let us يعني have 15 minutes.
حلو دكتور.
تمام دكتور، 15 minutes كويس.
ممتاز، يعني نرجع على 11 إلى 10 صح؟
بإذن الله إن شاء الله.
إن شاء الله، يعطيك ألف عافية. شكرا.
يعطيكم العافية.
دكتور بالنسبة للفيديوهات دكتور، ممكن تجرب تشغلها برا السلايد شو؟
حاولنا تو قبل شوي انا شغلتهم، خليني في البريك هذا احاول. طيب ان شاء الله
تمام. لانه ممكن تكون المشكله من السلايد شو لما تسوي فل سكرين للسلايد شو يمكن ما يطلع الفيديو.
طيب احاول.
لو سويتها على برا السلايد شو ممكن انها تفتح.
ممتاز. So I will stop sharing the slide. We will try ان شاء الله. ممتاز.
تمام، يعطيك العافيه دكتور.